back up to 46 and just revisit the Boussinesq. Just quickly as a refresher, remembering that the Boussinesq was really a fluids guy, and he's talking about how fluids have pressures at different, his was about different viscosities, but visiting this, how we have pressures induced in different directions from a vertical load on, in this case. So then 46, sorry, slide 47, then if you would please step through as we go, Trevor, shows the Boussinesq equation from the NS, it's an NS, Norfolk Southern document here, where P sub S represents the pressure at a particular point, active pressure from the surcharge loading, the railroad in this case, a live load surcharge. We won't go through all of the equation, but you can see on slide 48 where those, the alphas and the betas and the P sub S are all measured. So what we do is put together a spreadsheet, which I can share with you guys if you want, where you look at the load per square foot based on the width of a tie and the longitudinal load in the longitudinal direction, and what pressure that would apply at any point. So you put in the points at 1 foot increments or 2 foot increments until you can narrow in on the maximum pressure, which looks like this exhibit right here. And you could see where different tracks at different differences impose different distances rather impose a load of a different magnitude on the wall at various depths. They can be combined and typically are for a maximum load. It's a relatively conservative approach, but it can be used that way. So just a quick refresher on the Boussinesq method. It is one thing that makes railroad retaining wall design different than other retaining wall design, a unique portion of it. Let's step now into slide 50. There are basically a few types of external stability we want to talk about, which the first of which is global stability. You know, this is largely a geotechnical matter. Obviously, you know, in a lot of cases, retaining walls are geotechnical matters in and of themselves. But the first thing that needs to be considered is global stability. You know, what is the area like it around the wall itself, and what concerns might I have for a complete wall failure, externally speaking? So that is the first check, the global stability. And I'll point out on these different stability checks, there are different factors of safety based on, I guess you'll say, the likelihood or probability of a failure of that type, and generally what available information is available to you and the reliability of that information to make that calculation. So again, the first is global stability. Are you going to have a failure plane somewhere around the wall that would in turn basically collapse the entire wall, potentially, or a portion of the wall? Next is sliding. So just like the exhibit shows, you know, is the wall able to slide? And this would be due to active earth pressure. So again, the factor of safety is different here, a 1.5. So you basically take into account the friction between the bottom of the wall, the bottom of the wall and the subsurface around it. Also germane to this calculation is the passive earth pressure on the front of the wall. So obviously the deeper you put the wall into the ground, the more passive pressure you're going to have on the front of it, and less likely base sliding will be. So it's basically active pressure versus passive pressure in sliding the wall in that direction. Okay, very rare type of failure, but needs to be considered and calculated. The next is probably one of the most common failures. The next two are probably the most common, but the one we tend to focus on the most in calculations is the overturning stability. And you can see it has a pretty high factor of safety required with it as well. You know, we talk a lot about summing the moments around the point. In this case, you would sum the moments around the front toe of this foundation and calculate your overturning moments versus your resisting moments. And the gravity of the weight of the wall obviously being a major factor in that, and whether or not that wall can and will turn over. You see this kind of instances sometimes not only in retaining walls, but we consider uplift, if you will, as it's known on bridge abutments. Do we have a situation where you might have a corner of the foundation or an edge that is actually in an uplift condition, which is rare but also worth considering, which is better when you have deep foundations to as opposed to spread footing. Next is the external stability check for bearing capacity. Again, one that we are probably more familiar with, and checking, what is the allowable bearing stress, if you will, on the soil surrounding it, and what is the weight load from the wall itself and bearing on the ground. That being the bearing capacity calculation. So how much is available versus how much is loading it, and then looking at the factor of safety between the two. There are obviously ways to increase your bearing capacity in the soil through soil modification, different types of foundations. That's obviously a couple of ways. And also you can do other things like changing the dimensions of your wall. So if you increase the size of your footing, therefore you increase the area. And remember, P over A, as A goes up, the force of that bearing pressure goes down. So keep those in mind. Look at these bearing pressure calculations. Typically, this would be left to your geotechnical engineer. You provide them the geometry a lot of times. You provide and the loading. They will check at least the global stability and sliding type stuff. You might be called upon to check the other two. So just be mindful of that. Know that these calculations exist and need to be part of a calculation check. Let's move now to internal stability, which, for those on the design side, especially the structural design side, more familiar with. But think about these sorts of things as you change wall geometry and as it relates to your track alignment and other features at the site. I'm on slide 54 now, Trevor. Sorry if I've gone a little fast. Internal stability checks. Design and check bending for both the wall, stem, and footing, and then design and check shear, which people don't always think about shear loads in footings, and the big one being punching shear. We'll talk to that in a second. So the big one here, we think about checking bending moments, and if I can't really draw like I normally would in this type of presentation, but consider this. Where are the loads going? Where are the moments in this wall? And where does that deem that the reinforcing should be? And when you check that reinforcing, do you have adequate reinforcing to resist the loads? One that is commonly missed or not thought of, or maybe not checked in the right place, is in the footing. You think about where, so typically this load, and again I would draw it if I could, look at the loading on the heel of the foundation. As the wall tries to, I should say this, as the active earth pressure tries to push the stem or the wall over, and the passive earth pressure weight of the soils on top of it try to push the footing down, you have a very large moment at the interface between the top of the footing and the back of the wall, basically trying to peel those two apart. And that's a big point for, you need heavy reinforcing in the back of the wall for the moment going horizontally, and then you need heavy reinforcing in the top of the footing. In the top of the footing. Traditionally, we might think of that being in the bottom of the footing, but in the top of that footing, you would need heavy reinforcing for that moment on the heel. The toe is going to be different, right? You need reinforcing in the toe for the opposite load, where it's trying to push over and bend the footing in a smiley face sort of fashion, right? So you want to resist the smiley face in one direction and resist the frowny face in the other direction for the positive and negative moments in the footing. We don't typically think of footings a lot of times in a moment sense. Same is true on shear. So when you're doing a check for shear, you're trying to push that wall horizontally and the wall versus the footing. So you need to check your shear reinforcing in the wall as it relates to the footing itself, and then looking at shear reinforcing in the footing as well. Typically on the toe, right where the wall meets the footing, is a high point of shear. The big one that sometimes gets forgotten is punching shear. So when you have a heavy load on a pile, it's being resisted or tied together by the pile cap itself. Imagine piles projecting downward from this foundation. And so as you have those heavy loads, they're trying to, the pile is literally trying to punch through the footing itself, especially on the toe when it's in compression, and pulling out of that'd be a tensile load, not a shear load on the backside. We have a lot of details. It's common to put a hole in the top of the pile and put a hoop bar, if you will, or a V-shaped bar through the top of the pile to help with the tensile load. But in cases of punching shear, you need to think about shear reinforcing around the top of the pile and then the toe of the footing. be sure to check that. And you see this more commonly in buildings. You think about driving, a good example I can offer is driving into a parking garage. If you've been into a precast or cast-in-place parking garage, you'll see how a lot of times the columns where you park, by the column, take a look up, and you'll see that there's a thicker section, usually put off in a square shape or a 1-to-1 45 near the columns at the floor interface of the columns. That's due to punching shear for the same reasons we're talking about here in the retaining wall. All right, let's move to slide 55. So a couple of special design cases worth discussion and consideration. Temporary construction. When we get into temporary measures, we typically are dealing with different materials. So it could be timber in cases for a temporary wall that you might not use in the permanent, right? You can reduce, reuse, ARIMA allows, and other design measures allow reduced factors of safety because it has a shorter service life anticipated. That doesn't mean your loads are any less, it just means your service life is less. I will point out, just as a word of caution, a lot of construction, a lot of failures in retaining walls and bridges alike, and structures in general, a lot of those failures occur during construction for this matter. I think sometimes we're a little too, we don't give enough conservative approach like we might on a permanent structure as we do on a temporary structure, and therefore give it less consideration, but we need to do that and consider those factors of safety clearly in the loading. Not only loading, but construction loads that can be different or sometimes greater than your actual design loads, your permanent loads. Down drag. Anyone ever designed for down drag or know what that is? Offer maybe an explanation for others that might not. Anybody ever worked with that? If not, maybe folks are actually muted. I don't know. I'm sorry. Down drag is essentially negative friction. So what happens when soil that you may have built upon starts to settle along the face of a pile? What you're getting is extra loading on that pile. Where normally that pile is used for friction to carry the load, here you're adding friction or dragging it down by putting additional load onto the pile. So you need to consult with your geotechnical engineer and question them about, do I have any anticipated down drag or negative friction in the piles as I'm designing them for my loading, whether that's steel piles, concrete piles, any kind of friction pile. If it's purely an in-bearing pile, it shouldn't have as much of an effect, but you need to check the extra additional loading from the negative friction. Cofferdams and causeways are essentially retaining walls. That's what you're looking at here a lot of times is when you're putting a cofferdam up, a sheet pile wall, it's a special design consideration for a temporary structure. Be mindful of that. Drill shaft excavations, there are times when we need to use retaining wall type structures in and around drilled shafts. It could be the casing itself, which is essentially, a drilled shaft casing is essentially a circular retaining wall. You're retaining material from caving into the hole, and it works just like a retaining wall. So be mindful of those in design cases. All right, let's move to slide 56. We have a lot of tools at our disposal in Microsoft Excel spreadsheets. I have one for live load surcharge that I'd be happy to share with you guys if you needed it. MathCAD is a common. I know a lot of the folks in our Kansas City office are very fond of MathCAD and use it, a couple of templates that we have there for these purposes. Then there's software that's for sale, PyWall, LPile, etc. LPile is one that we commonly will use and or offer loads to our geotechnical consultant to use in their version of LPile for their analysis. And GOP&P, if anyone knows what that is, you get big bonus points, but that's good old pencil and paper. You know, there comes a point where you need to sit down and put your good old pencil and paper to use, and my caution is, and why I say use the good old pencil and paper, is if you can't do it on pencil and paper, you typically won't understand the analytical tools as well. And I caution you, I call it F10 syndrome, where it becomes easy a lot of times to put our input values in and press the F10 button and get the result. But you need to be able to calculate things and give it what I call the snip test. You know, once I've done this run on my data, does it make sense? Sniff it. Does it smell bad? Am I getting some crazy factor of safety? Am I getting some unusual load case or load scenario that doesn't make sense? And what can we do or should we do to change that? So again, it helps a lot of times to just put pencil to paper, walk through the calculation for yourself, at least one iteration of it. Where the software helps us a lot is doing multiple iterations. It can save a lot of time, but nonetheless it requires a lot of work. Additional resources, one of the best that I found, there's two here that I really like. One is the Caltrans Bridge Design Specifications. Yes, it's California. Yes, it's different in some ways, but they have a lot of good references, exhibits. They have spent a lot of time and money on those design manuals. So pick those up if you need them, a good source of information. The other one is NAVFAC DM 7.1, and that is it's an old publication. There's 7.1 and 7.2. Basically, these documents were written for a young Army officer in Europe designing bridges and retaining walls on the fly in combat. So you have a little bit of data. It's a lot of charts and darts, but it's probably pretty conservative in the end. But it allows you to use what's available and work through things pretty quickly. It's a good resource for a lot of the information. Next is I want to offer you guys a design example. Gabion wall design. Just want to step through quickly because this is becoming more and more common. And I offer this just to walk you through a simple design. You can use this as a reference. Even us alignment people, so to speak, might need to do a wall design at some point. This is a very simple way to estimate some stuff and what you might need in a wall. So there are numerous examples offered. There's ways to find these examples through different sources, whether it be industry publications or professional associations, and just even manufacturers and vendors of these types of materials offer example calculations to be used. And I just want to step through this. Not that we're going to get in terrible detail, but the point here is it's a very simple approach to a gravity wall, and it's a transferable concept. If you can apply what's used in this calculation for a simple Gabion wall, that same calculation and logic can be used in a gravity wall of almost any type. So take a look at this real quickly. The Gabion wall, the sequence is a lot like we've talked about in the original sequence. You start with the basic sequence of the iterative, what's my geometry, what are my loads, step through this. Determine, check the resulting resisting moment versus the overturning moment. Check sliding resistance versus horizontal forces. Check resultant force location within the middle third of the base, and we'll talk about specifically what that means, and then check bearing pressure and repeat. So just keep going through that iterative process until you get resolution with something you like in the sense of what works. Okay, so that looks like this, right? Stepped front face. These are different Gabion walls, and just to be clear, I'm on slide 58. If you want to look quickly at 57, I think probably all of us know and understand what Gabion walls are. They're basically wire baskets filled with rock. It exploits, basically heavy friction and a heavy load of that material. They're really easy to come by. Railroads like them a lot because they're quick and dirty, fairly inexpensive, and universally available. So slide 59 shows a couple of scenarios with a Gabion wall. Example calculation here, A and B, we have a stepped front face and a stepped back face, both of which are fairly common. It probably looks better to have the front face as vertical or stepped back face, if you will. That's probably the more common, what we see and think of. Think pyramid versus retaining wall. It's kind of the same idea. Do you have the steps on the front or the steps in the back? And then you'll notice that this is actually at an angle. Typically, it's not uncommon to help us in the design effort to tilt the wall a little bit. It's not exactly vertical, although it probably could be. It is obviously on gravity walls, concrete cast-in-place gravity walls, but it's not uncommon to tilt that a little bit to take advantage of that loading. Next, then, let's go to slide 60. So if you know your geometry, let's just say that I need about a 9-foot wall, and I have this loading out beyond my wall, and this would be common, say, maybe not where you have railroad close by, say that you've got some sort of step in your site and you need to make this elevation change to protect, say, an existing parking lot or an existing utility. You need about a 9-foot step. So I'm going to estimate, I'm going to go to my manual and see what kind of gabion baskets are available. It's pretty common that they are 3 feet high, anywhere from 2.5 to 3 feet high or tall, each one. What sort of widths can I use? And they step them in usually 18-inch increments, as you can see here, 6 foot to 4.5 to 3. So they're stepping in 1.5-foot increments and 3 foot long, which is pretty manageable. Not that you're going to pick it up, but you can set a basket and then fill it with rock, set a basket, fill it with rock fairly commonly. Or fill them up and move them with an excavator, for instance. So you look at the different variables here. You estimate your approximate foundation at 6 feet. You estimate your beta angle that's at 6 degrees. In this case, it's tilted, and it's 9 feet high. You enter, this calculation, given design example, what are my variables here? H is my height, is 9 feet. What is my surcharge? I'm going to calculate that, for instance, in this case, at 300 PSF may be related to a live load surcharge from a parking lot, to say that the vehicles can park there. A common way to do that is simply to add 2 feet of fill. If you say my wall is really only 9 feet, but I'm going to estimate it with 11 feet of material behind it as an extra load or a surcharge. So what's the back slope phi angle, alpha angle rather, that's 0. Back face slope, -6. Soil friction angle, you can estimate this, the phi angle. You can get it from a geotechnical report, and I'm on slide 61, I meant to mention, Trevor. You can estimate that. You can pull it from a report, look it up at a table. But if you're generally in that 30 to 35 degree angle, you're going to be, depending on your soils and types there, you're going to be pretty close. You could go to NAVFAC, you could call up your geotech buddy, whatever you want to do to come up with a decent number on that. The soil density, 100 pounds, 120 pounds per cubic foot. Gabion fill density at about 100. And yes, rock is heavy, but it's loose, so you're going to estimate it 100 pounds per cubic foot. And then my bearing pressure, soil bearing pressure, in this case is about 2 tons per square foot, which is actually a pretty good bearing pressure. 4,000 PSF is pretty decent. But if you wanted to be conservative in softer areas, you could even go with 1 TSF, which would be about 2,000 pounds per square foot. All fairly generic numbers that you can derive from a report. Then you basically calculate the vertical load, horizontal pressure using Ka. You may calculate it, but I would simply, again, look it up. You're not going to go through this complicated equation. You shouldn't have to. But you enter the PA value with your alpha number, your case of A number, the other values you have already, the WS, weight of material, your height, your Q value. You enter that equation and then calculate equations 9 and 10. So you're going to calculate your E value, which is your eccentricity. That eccentricity will tell you what is the center of your load. Where if you were to load this wall like it is right now, where does the centroid or center of that loaded wall fall? What you want it to do is to fall within the middle third of your footing. If that eccentric load is what I'm trying to say, if that eccentric load falls within the middle third of your footing, you are safe. That is a safe location for it, presuming you've calculated it properly. To get to your middle third, what you're saying is negative B/6 to B/6, right? So that takes out the 2 endpoints, the 2 sides, and puts it in the middle of that foundation. And what you can do with that is play with the B value. How wide does my foundation have to be? Is it 9 feet? Is my B value 9 feet, 6 feet? Can I get a shorter wall, a narrower wall? What you're going to find is pretty quickly that as you narrow it up, the height is going to overtake that number, and so it's not going to work in your favor. So calculate that value. Once you know the eccentricity, then you calculate your maximum pressure under the base, which is a simple, essentially P/A value, force over area, from equation 11, and compare that to your bearing pressure. If I've got the factor of safety I need in the bearing pressure and my resultant forces in the middle third, I should be safe with that foundation. This same logic applies to, retaining walls, cast in place concrete retaining walls, gravity walls, gabion walls. It's the same basic logic that can be used for any of those analyses. Okay? Let's go to slide 64. This is the same concept. What I'm trying to offer you are some tools. Okay, so I'm giving you a tool on the gravity wall side, simple retaining wall. Let's give you a tool on the deep foundation side of the house here. So sheet pile design is not, you can apply this, it's numerous, there are numerous examples available. The one I'm going to offer here is from the U.S. Steel Design Manual, which is basically a vendor, industry organization trying to sell steel piles in particular. It's a simple approach. It's a little more complicated than the previous one, but again, it's a very simple approach. You can print this presentation and use it to walk through a couple of the calculations. Transferable concepts. The point is, if you can design, if you can apply, you can take these same calculations and apply them to, say, a soldier pile and lagging wall. The concepts are not that different in a lot of ways. So in this case, move to slide 65. So I'm offering here, you can actually look up the steel manual and get these calculations for yourself, but you can see on slide 65, it offers 4 different types of walls. So you got a cantilevered sheet pile wall, an anchored sheet pile wall, a braced cofferdam, which is essentially a sheet pile wall with the whalers and struts, and then finally the cellular cofferdam, which is essentially a boxed retaining wall. So I'm going to offer, and those are the examples in the book. You can see, in fact, I'll point out, none of those example calculations are very long. Right, you've got, and then you got different soil types. Am I in granular soil or am I in cohesive soil? You're talking about 5 or 6 pages worth of calculations. Sorry, let me get rid of that. So the one I'll offer on slide 66 now, Trevor, is design of cantilevered sheet pile wall in granular soils, so sandy soils essentially, resultant pressure distribution. So the first thing you'll need to do, and you can imagine looking at this shape as if it were a beam. It just happens to be a vertical beam. So look at the pressures on the wall and then calculate moments along that wall and ask yourself, where does it bend? Where is there bending moment in the wall itself, and how does it bend? So you say, okay, you lay out your geometry. I need a wall. I have a step down, a wall that needs to be about 25 feet from my track, 35 feet from my track, so therefore probably very little influence from the track. It needs to be about 14 feet high. I've got a low water out in front of it. My original ground line, and this would be like a top-down construction. So you estimate these values where your gamma, meaning your weight of soil material, is about 115. The previous one was about 120. You'll find as you do these more commonly, you see repetition in these values. My gamma prime is 65 pounds per cubic foot. That's the weight you're basically allowing for your soil, your pore pressure in the soils. Phi angle is about 35, close to what we had before. Then you look at, I'll skip over the next one. It's a simple, gamma over phi. The next one is your case of A and your case of P. It's not uncommon, whether it's a sheet pile wall, a gravity wall, abutment, whatever. It's not uncommon to need both values for case of A, active earth pressure pushing on, and passive earth pressure in front. And that they help you. Obviously, the passive pressure typically will help you, and the active pressure works against you. But together, you need them, the two of them, to counterbalance in a lot of ways. In this case, it's doing both. It can be good and or bad. But you have a figure. There's a figure than otherwise in the table. In these calculations that offers those values for you. Again, you can get them from your geotech report or from typical values. So what you're going to do then is try to evaluate, pick a point, and we'll look at the next slide here in a second. But you're going to pick a point to sum your moments around. Let's move to slide 67. So your point of origin you picked is, 0, 0 primed, or 0 sub 1. You're going to pick a point and try to work your moments around that point. So you see from, I'm going to back up to slide 66, but think of this as your typical moment diagram in statics class, for those of you that have had that class. But you'll look at this as a simple approach to where's my loading, is it active or is it passive, and what sort of moment does it induce into the pile, okay? How deep, the question most times with a sheet pile wall or any kind of deep foundation typically is how deep do I have to go? And can I get that deep? A lot of times you may have shallow rock and a sheet pile wall just simply won't work. You have to take other measures, whether that's drilled shafts or socketed piles, other measures. But if you have a deep granular soil like we're discussing here, like what we have a lot of in Charleston, for instance, if you have that, the question will be, how deep do I have to go to economize my wall? The rule of thumb would tell you about, for every foot up, vertical wall, vertically up, you need about 2 feet going down. That's about a rule of thumb, and that's typically where I start the design. I'll start guessing at, okay, if I have a 10-foot wall, I'm going to have a 30-foot pile. I'm going to go 2 down for every 1 up, and I'll start my evaluation there. Okay. So in this case, you're looking at summing moments about these points. You're going to determine the wall pressures. So calculate passive pressure, active pressures. Where am I loading this wall, and how? What movements are induced? Okay. After you have those pressures, you go to slide 68. Once you get those pressures, you can go basic statics, right? Slide 68, equation 1 at the top of the page, summing forces at H, right, equals 0 in terms of the areas. So calculate those areas. What are the pressures? Solving for Z is what we're doing here, is trying to get to a depth, right? PE minus PA, and I won't step through all of these, but you can see what's going on here. You're solving for this value, and then sum your moments about any point. Any point is 0. So in other words, you don't want movement. You want those moments to equal 0 in the wall. So moments about F, you're going to calculate those moments up or down. Method of solution, assume a depth of penetration D, which we said 2 to 1 is probably a decent place to start. Calculate your value for Z, right, and then substitute your Z value into the sum of moments and check if it's 0. Adjust D and recalculate as necessary. And you can see where a spreadsheet or a computer program would be very quick to help you with this, right? But that iterative process, okay, I'm going to guess D at 20 feet. Well, that doesn't work. Let me guess D at 22 feet. Well, that works, but it's a little more than I need. Let me guess D at 21 feet, and kind of go through that process again and again till you arrive at a solution, which I'll make a point. It could change along the length of the wall. Let's just say that my wall goes from 14 feet high at one end next to an abutment, let's say, down all the way to 6 feet high or 4 feet high at the other end as it tapers up. Say you've got an undergrade, railroad bridge going over a roadway, and you need to build a wall that's pretty long. So you might be changing this. So you'll take the wall in segments or sections and run this calculation several times along that wall to get an optimum design, using as little sheet pile as you can get away with. All right. So then, in the first case, I'm on slide 69 now to finish this conversation, this calculation. Try D at 10.5. Z comes out at 1.6 feet. Plug in 1.6 into that equation. Sum the moments about F. All right, well, that works miraculously on the first try. So you say, okay, use D of 10.5 feet, right? Which is, to me, a little shallow, but duly noted. All right, so move to slide 70. Let's talk a bit about wall construction. So part 3, construction. I'm on slide 71 now. Trevor? I'm just going to step through these slides, talking to kind of give you a sense and show you some photographs. Now that we've talked through the design portions of it, kind of a better understanding of the vernacular, show you a few cases where these walls have been used and how they might be used. All right. So when you look at these slides, look at design of the wall to be considered. Was it temporary or permanent? Materials being used, the method of construction, meaning top down versus bottom up, and why that might have been. And then finally, construction phase, keeping track in service and minimizing service interruptions. That's always paramount to what we do to serve the roads that we're building. So number 1, temporary retaining walls. You probably saw this picture previously. This is basically a cellular cofferdam, like we described in that sheet pile calculation. It's a big box, and it's loaded on all 4 sides. and as you're building it, you're decreasing your resisting moment on the inside and increasing your loading moments on the outside. So we put in wailers and struts, and we build these walls as we excavate them down, adding struts. Okay. Slide 73. Temporary retaining walls again. You know, it's not uncommon to put them around substructure units that may be existing, or in order to build those substructure units as we bring them out of the ground. And it's also not uncommon, I'll make a point here, is to leave that wall in place permanently and just cut it off at the ground line and backfill in between it. So you look at this photograph in the center of 73. So what's essentially happened here, the contractors come in and put a sheet pile wall around what was a foundation, or in this case a crash wall, to be able to build that. So you've got to get in the hole and tie my reinforcing, put in my forms, potentially come out of the ground with that segment. So when that's done, what do? Do I going to extract the wall? Maybe. But if it's sacrificial and I don't want to do damage to the track, I can just take a torch and cut that wall off at the ground level or a foot below. Before I do that, I can backfill the hole with material, cut it off, and call it good. Okay? Actually reduces the loading to your permanent foundation. Slide 74. Gravity walls, bottom-up construction. This is not unlike a gabion. These just happen to be precast T-sections that if you have a place where you're building, widening an embankment to, for instance, build a second track or shift an alignment, you can go to the bottom of that foundation, put your founding material. In this case, they put in some drainage material behind it, dropped in the precast T-sections. In this case, they put in mechanical stabilizing filters, if you will, between some of the layers to get it back into the wall, and then constructed the wall up from there. You can see as this bottom-up construction comes to the top, and it's going to be a really tall wall when it's finished. This wall will be over 20, 25 feet high. 75, gravity walls. You can see a couple of instances of this. The one on the top right represents a pretty narrow hole in the wall, if you will, where precast blocks, panels, can be placed on top of each other with keystones between them, shear keys, if you will. They keep them from sliding on each other, and then the foundation itself, and then backfilled for the retain the material behind the abutment rather. Another one, case at the bottom of precast wall, similar to the T-wall you saw a moment ago. A simplified wall on the bottom right. Looks pretty nice to me, with form liners on the face of that gravity wall with shear keys shown on the top. Pretty simple approach. Slide 76. You can go pretty quickly here and kind of showing. This is between two gravity walls on the right-hand side. You're looking at construction. In fact, it's stepped down in this location, but constructing between two gravity walls, basically coming up, bringing the grade separation up as you go. Slide 77, kind of belaboring at this point, but you can see in the picture on the right, there are a series of different foundation types. You have piles protruding into the air for what will be a bridge foundation, right? Those abutments will be resting on deep foundations, while adjacent to those you have gravity walls, precast Ts, that are being built to bring the grade up as well. This ultimately will be a grade separated structure, eliminating a grade crossing. Slide 78. Let's not forget masonry walls. There are a lot of them in service. For those of you who got to attend the bridge presentation, we talked about how they were built, the dry stack method. The dry stack method is not for stone masonry walls is not unlike the gravity walls, precast concrete of today. Instead of cutting the blocks, we're just casting the blocks instead. It's a lot more efficient. This method is used a lot of places around the railroad because it is quick, it's efficient. I'll show you an example of Norfolk Southern 47th Street Intermodal Terminal in Chicago. The beauty of some of these walls, the T-sections can actually be laid on a curve, and you can decorate them. You can see on the right-hand side, you've got the NS logo and the form liner to show, make it look a lot nicer, especially in urban areas where it might matter to surrounding communities. Finally, I'll show you on slide 80. I said finally, I'm not done with the gravity walls, I thought. This is a relatively unique and new technique. It's basically a cellular type of structure where you take a flat plastic sheet. It is zip welded or heat welded, if you will. The plastic is welded to itself, where if you push on it, I'm not describing it terribly well, but if you push on it, you open a cell. Imagine kind of like a deck of cards when you shuffle them and you kind of do that funny move where it opens a cell between the cards. You're doing essentially the same thing, except you open that cell and you fill it with rock, and then you lay another layer. You set it back 6 inches and you open another cell and you fill it with block, to where you have essentially a built-up gravity wall. You can see this in the detail on the photograph on the lower right, but it's a very simple approach. You can see this has been used on a bridge approach to raise the grade in the area and keep it off of that tree, other protection, keeping it off additional right-of-way. Slide 81. This is a pretty sophisticated but pretty tall reinforced wall where you have surcharge on top and fill material where we've used a large pipe section surrounded by precast concrete elements that also included geotextile, geosynthetic reinforcement, if you will, going back into the subgrade behind the wall to help stabilize it. Not unlike tieback anchor walls. Next, gravity walls, more of them, I won't belabor it. 83, crib walls, gravity walls, again, it's a type of cribbing. What I'm getting at, kind of belaboring the point a little bit, but there's a lot of mousetraps when it comes to gravity walls and retaining walls. Fairly simple approach, fairly simple design that can be done, although it does require design, some effort there, and detailing for the appropriate site conditions. All right, finally, let's go to slide 84, secant pile walls. We talked a little bit about this in the design sections and how they were built. You can see, if you look closely at these pile sections on the upper left-hand photograph, they're notched, right? And that allows the contractor to put a bar. You can actually turn these piles. They'll lower a bar into the pile. It slips through that hole, right? And then they can twist the pile into the ground, or actually use it like a hook and pull the pile out of the ground when they're done, so they can be reused and progress the work. So you're seeing some of that work in the lower photograph, where a secant pile wall, secant section, if you will, the metal is driven in or vibrated in, excavate it, fill it with concrete, pull it out. Do the same thing over and over and over, and then when you're done, come back and like on the right-hand side, put in a section of welded wire fabric and shotcrete the face of it, and then in the final product you see on the lower right. So obviously a very good top-down construction method. Yes, it takes a lot of material, but it doesn't require a lot of work. You can do this work from above without impacting a lot of impacts to surrounding areas. Slide 87. One of my favorites is the soldier pile wall, where again it could be a piece of rail, it could be a piece of pile. If the rail filled with timber cross ties, that's a pretty common method. It's not the most enduring, but it's one of the most simple and one of the most commonly, two of the most common, if you will, materials on the railroad. Piece of stick rail somewhere, kind of a lot of that laying around, and then a couple of cross ties to put between them, heavy ties to put between them is a pretty common method. If you want to get obviously more sophisticated, you'll go with soldier pile, H-pile sections like you see here. You could also use concrete pile sections where steel piles may not be appropriate or useful. In either case, you can put concrete planking, precast concrete between them, and build a decent wall pretty quickly, and fairly inexpensive as well. Next, slide 88. Just by the sheer size of this wall, you can see it is a very tall wall, just if you look at the context and the size of the folks next to it. This is tied back soldier pile wall. Same approach, same method, where you have a vertical soldier and some soldier pile, and then lagging in between it, whether that be temporary or permanent, using, in this case, soil nails or nails anchored into the wall in some fashion. 89, using an anchored wall method, soil nails, where it requires basically you're just the soil is your face of wall until it is shotcreted. But until then, you're basically inserting a wire fabric and soil nails into the ground. Sophisticated, a lot more sophisticated design, geotechnically speaking, to get that soil nail to work in whatever substrate you might have behind the wall. It's pretty common you run into some bad layers. If you have a bad layer, you want to be able to go in there and get through that bad layer, and don't rely on that bad layer for any type of your structural resistance on the soil nail. Slide 90, anchored walls, again, soil nails, showing a few examples of how and where they might have been used. The one on the lower right is actually, in fact, the center one. Maybe I'll freeze these. I'm trying to recognize a Worcester project up in Worcester, Mass, intermodal facility. 91. Sorry, I'm trying to go. The mouse is acting funny. On slide 91 in the lower right, it shows you a close-up of kind of what that wall would look like, or does look like once it's built. It's pretty ugly. Frankly, you have to have these holes that drain from it. You have to have all these nails protruding through it and the plates that go on them. So it's not the prettiest of systems, but it is pretty economical in the sense of can be built and built quickly, and then you can face it with something else. If you really care to make it look nice, it can be fixed in that fashion. Slide 92, these are sheet pile, similar approach, a sheet pile wall with anchors. So instead of having a concrete shotcrete face, you can have a sheet pile face as well. 93, looking at this Hampton Roads facility, you can see a couple of cases where you had anchor walls in the system, right, whether mechanically stabilized or otherwise anchored. Slide 94, MSE walls. You know, generally we say that the railroads don't like to use MSE walls, and generally they don't. What you don't want, and the reasons why, a couple of reasons, namely if you have a mechanical disturbance. So in other words, if you come through with a machine that has the potential to grab a section of the stabilized material, the geosynthetic fabric, right, you have the propensity to be able to damage that material, and you don't want to do that. The other is that sometimes, and most often, these materials can be made with plastics, in which case if you had a locomotive derailment and you lost fuel, or other kind of derailment, if you lost petroleum chemicals, a lot of times that chemical can decay the other plastic product, and therefore you have lost all stability of the wall, potentially. So that's another reason not to use them on the railroad. That doesn't mean that they can't and won't use them in adjacent lifts where it might be necessary. Okay, so that's another use of them. Slide 95 shows the lower picture on the right, and the section on the left just shows a good example, construction example of MSE in process. You have wires, you have fabric. It could be both or either, or can be used for construction for that mechanical section. Then slide 96, anchored walls in rock cuts. Kind of go back to the soil nail idea, but in this case being placed in a rock cut, which is nearly vertical. So it's a pretty easy way to do that. Cantilevered section, slide 97. I do like this one for a lot of reasons, but on slide 97 it shows a precast cantilever wall. You can see that your heel of your foundation is pretty short in comparison to your wall itself, which makes it a pretty astounding little wall in that regard. Very economic design. You know, you can put the face of the front edge of these walls together and place them pretty tightly on a curve, straight sections. It can go pretty quickly. You can see they've laid back the slopes behind it on the slope on the right, laid those slopes back, placed the wall, set it down, backfill it, call it good. It can be done pretty quickly, but still presents some challenges in the construction methodology. Slide 98, cantilevered walls cast in place. You do the same thing. This is actually, may look familiar to some of you. It's actually in Worcester as well, where I'll show you these two in sequence. 98 and 99 was a bridge that was basically abandoned, Putnam Lane, I think was the name of this one, up in Worcester job. And you know, since the bridge was there, it could be used for, as a utility corridor, which on slide 99 shows that utility corridor in place once it was finished, what's kind of cool about this, actually on slide 99, you have two photographs showing the same wall, one from the inside looking out, where those penetrations, and some of those penetrations are 4 foot in diameter. We have big utilities, water mains, sewer mains, all kinds of stuff. This bridge was ultimately used as a utility corridor. On the lower right, it shows that same wall from the outside after a gravity wall had been placed in front of it. So where those utilities came through the wall and then just dive underground, had that wall, second wall there to protect it. So it shows two different wall types in one photograph that are separated by just a few feet, mere feet. And then slide 100 is showing cantilever wall cast in place, in construction there as well. So and that's a case where you didn't want to use, you had a grade change elevation. If any of you worked or knew about the Worcester site up at Mass, it had a lot of relief in a very small site. Had a lot of walls and a lot of different kinds of walls. In this case was a spot where we couldn't use, say, an MSE wall because of the loading that was on it and proximity to the railroad, but it could be used as short cantilever retaining wall. And that, my friends, concludes our presentation for retaining walls. Are there any questions? Trevor, are you still there?
Yes, sir, I am.
All right.